can we continue with the new header on kinetics? Okay. Now, kinetics, right? Definitely you will be dealing with time. Okay, so please be very aware that when you see the stopwatch and there is a plotting against time, there is a good chance it is a kinetics experiment. Okay, now how does it manifest as an experiment? Okay, sampling, so at different time intervals you draw out aliquots and you titrate. Okay, please be aware, people. When you have kinetics, okay, you will only have one sample at that timing. Correct? You only draw out one and you just titrate against that one. So that means, right, you have to do a good job. Please do not rush, do not overshoot. You understand what I'm saying, people? Okay, right first. Okay, note, sometimes the header will look like this. Okay, sometimes the header will look like this here. Okay, where you measure, this one is gas collection, okay, but you can have different time intervals, different aliquots, and what is the burette reading. Okay, like the one below at different time, the one below is the one that we did recently. Different time, TD, final, initial, and then of course volume FA1 use. Okay, you might want to note the general steps as well. Usually you start the reaction and of course you will start the stopwatch upon mixing. Okay, at different time intervals you will sample. Okay, so before time t an aliquot is pipetted, and then after that, before you titrate you must quench. Okay, so quenching of withdrawn samples before titration. Okay, quench to stop the reaction. Please also recall the different ways to quench. Can someone help me with this? Aaron, what are some ways that we can use to quench?
Large volume of ice cold water.
Okay, large volume ice cold water, what does that do?
Dilutes the mixture.
Dilution and?
Slows down the rate of reaction.
Dilute, slows down, okay. Ice cold water, what else does ice cold water do? Large volume is the dilution, right?
Slows down the rate of reaction.
By lowering.
By lowering temperature.
Thank you. Okay. Different ways to quench. You might also want to note down. Okay, you can either dilute large volume of water or a solvent. You can lower the temperature to lower rate. Okay, like the ice cold water that Aaron mentioned. And the last way is to remove one of the reactants. So, for example, you have an acid catalyst. You throw in a large volume of the base, okay, to remove the acid. Okay, example, add OH minus to remove H plus. Okay, so please recall the different ways that we use to quench. Katie, can I help you? Sampling. Before T1, an aliquot of the reaction mixture is pipetted into a conical flask. HI, make it bigger. Okay, I'm going to escape and make it bigger, okay, Kate? Is this big enough or still not big enough? Questions? Okay, now so most of you are done with the writing, so just to make sure we have all heard this, okay? For sampling, because it's at different time interval, right, you can only afford to draw out once. Okay, unlike the normal titration, you do 2 and then you wait until you get consistent. This one you only draw out once. So please make sure you do it properly. Okay, now if the data comes out to be really off, circle it and then ignore it as an abnormality. Okay, but before that, people, what is the criteria before you decide to ignore it as an abnormality? Anyone can recall? This point must be how far away? Huh? More than 4 squares? What kind of squares? Like the small, any more guidelines to this small square? Small square is in how? Vertical, horizontal? Hey, if I have a line like this, right? So my points are maybe somewhere nearby. If I have a point here, okay, and you choose to omit it, this point to be considered a valid abnormality, you firstly look at the perpendicular distance, and this must be at least 3 small squares. Okay, make sure you remember this. Okay, why am I saying this? Because in some of the practical graph earlier, you ignore a point, but a point is actually less than 3 small squares away. So it is not a valid abnormality. You understand what I'm saying? Okay, so again, if you want to see as an anomaly, okay, it must be perpendicular distance at least 3 small squares away from your best fit line. Are we clear on this, people? You should write it down now. You want to write it down? Now, next thing. Now, because you only have one solution to titrate, right? How do I know that I'm nearing the endpoint? Can we recall? What happens to the indicator colors? So, for example, I'm titrating with KMNO4, right? Every time I add the purple should discharge almost immediately at the start. But towards the end, there will be lesser of the reactant. So what happens to the pink? It lingers longer and longer before it finally goes off, right? Correct? At the start, you can see that the swirling is very fast. It goes off immediately, okay? But as the reaction progresses, the pink stays longer, but it still discharges at the end of the day. So the longer it stays, it suggests that there is lesser for it to react. That suggests you are closer to the endpoint. Do I make sense to you, people? Do I make sense? Okay, so please make sure you are careful, okay? If it's starting to slow down in decolorizing, then you're nearing. So one time, let's try to hit a 1 drop. Also, okay? Can? Now, one last reminder for KMNO4, I don't think it was there. For KMNO4, you need an acidic medium. And if you remember, we always add the acid in excess. Correct? Now, I'm not sure if some of you remember, in the past when we do KMNO4, if you keep flushing the KMNO4, it means you add very fast. Instead of it decolorizing, what do you see? Brown. It turns brown. Correct? Some of you end up with a brown PPT. So what does getting a brown PPT suggest to you? Say again? Not enough acid. You have actually gone into the basic medium where you get MnO2, the brown black PPT. Correct? Okay, so please be very careful when you are doing KMNO4. If you are given, when you are adding, please make sure you add slowly at the start. Let it decolorize. Means you have gone into the acidic medium, then you speed up on the titration. Do you understand what I'm saying? Because once they're in the acidic, they will stay in the acidic. They will not go back to the basic. Similarly, once you form the brown, no matter how much more acid you add, it will not help. You just have to pour off and restart. You understand, people? Okay, so again, a reminder for KMNO4, please make sure you add slowly at the start. Let it discharge first, decolorize, then you speed up on the adding. Is that okay? Everyone clear on this? You might also want to write this down. Okay, reminders for KMNO4. Okay, so in an earlier part, you have the redox titration, right? You can write it down there. Alright, otherwise, can I continue? Okay, I'm going to continue, people. Now, the next one is this, plots against continuous sampling, concentration against time. Alright, okay, so this is what you will see. Con against time, this is usually the kind of graph you'll see. The first one is a reactant time graph. Oh, sorry. This is a reactant time graph. Okay, this is a product time graph. Okay, product will start with nothing, right? So you will start from 0 and then it slowly increases and it plateaus off. Alright, concentration against time. This is also the one that will allow you to find order, okay, via constant t-half. Okay, this is really the theory already, people. Con against time graph. Okay, zero order, how do they look like? First order, how do they look like? And of course, other orders, how do they look like? Okay, so maybe in your own graph, can you add in, people? How does a zero order look like for reactant? How does zero order look like, people? Zero order means does changes in concentration affect rate? No. Rate is shown as what on this kind of graph? Rate is the gradient, right? So if rate doesn't change, I'm looking at a constant gradient regardless of changes in concentration. Okay, so I should be looking at a downward sloping line. Alright, then first order, curve with constant t-half. Any other orders will be curved without constant t-half. Okay, add in the zero order. When you revise, you should revise this. Alright, now I'm going to move on. Just take down the general shapes. Okay, you also want to note that for first order there is constant t-half. Okay, so you might also want to write down construction lines. Okay, label t-half equal to what? Okay, I want to see the value and of course label t-half with arrows. Okay, I must see construction lines. I must see the t-half marked out with the double-headed arrows. Okay, and I also need you to specify t-half is equal to what? Alright, so we frequently have students, we frequently have students that write this, t-half, and then t-half, and you don't tell me what it is. Okay, so make sure when you're marking out the t-half, you write down the value, 14 or 15. They are approximately constant, because that's very close. So conclude first order. Questions? I think you should be almost done with your revision, right, by now. You should have revised significantly. Okay, let's continue. Continue, Now, next one, in kinetics, there is still this part of clock reaction. Okay, experiment 9 and 14. Clock, basically you're measuring color changes over time. Okay, so there must be a color changing reactant and the amount is constant. Okay, so for example, your thiosulfate, time taken for the thiosulfate, thiosulfate with starch. Okay, for clock, please allow me to remind you, usually you will see this, okay, because this will help to keep V total constant. Okay, so usually they give you one experiment, then you will repeat with a few other volumes, right? So when you repeat with a few other volumes, sometimes they will tell you the volume, sometimes you decide your own volume. Okay, so if you need lesser, please make sure you top up with DI water. Alright, they will tell you, so you need to have this column here. Okay, again, the first column, sometimes they will tell you, sometimes they will get you to decide your own volume. Okay, either way, as long as you keep total volume constant by adding water, you should be okay. Questions? down the 14 and 9, okay, if you're not very sure about clock, okay, they can go back and review it. Okay, now this is the best thing for you to bring on Wednesday because it has actually summarized everything, right? Okay, on top of your planning, of course, so maybe you have to bring in some of your planning notes, alright, on Wednesday during the morning. You will wait for a while in the morning, right, from the reporting to the experiment. Can I continue? Shall we continue? You need more time? Okay, good. Let's continue. Now, percentage uncertainty. This is what you are very uncertain about. Alright, let's just review it. There are two kinds of uncertainty. One is the absolute tag to the apparatus. Okay, so for example, the period is plus minus 0.05. Okay, then you have the percentage uncertainty where you have the absolute expressed as a percentage. Okay, so the absolute over what you measure using the apparatus times 100%. Okay, now these are the common ones you need to note down. For burette, plus minus 0.05, but because I do two readings for one value, I will multiply by 2. Okay, similarly for the mass balance. Okay, mass balance, you will either tear first or you will take with the solid and after emptying. So that's why you times 2. Okay, take twice to get value. Okay, example, you have bottle plus solid. Okay, and after emptying. Alright, even if you tear, people, tear is considered one reading. Okay, so you will times 2. Alright, thermometer on the other hand, we don't read twice. Whatever is the value, we just read it once and we just record. Okay, I always get students that forget to times 2 for burette. It has been a while since we last did that. Okay, so please make sure you review this. Questions? Okay, these are the common ones that we will use. If they have stuff that you aren't usually exposed to, for example the pipette, then they will tell you pipette is usually plus minus 0.06. Okay, otherwise you will need to know the mass balance and the burette for sure. Can I continue? Okay, note down the main things. Alright, now I'm going to continue. The next thing I have for you is the kind of calculations we do for percentage uncertainty. So if you recall, there are two kinds. One of them is where we add everything together, sum over the total volume. Okay, one of them is this, the A plus B plus C over VA plus VB plus BC. There is another one which is like this, VB plus C over VC. Do you remember these? Okay, can we also do a quick recap? Okay, don't look at the script, don't worry. Okay, a little different in how we teach this. Do you remember when I used the first one here, where I sum all uncertainties over all the volumes. The volumes are related to each other in what ways? An addition or a subtraction. So for example, I have a reaction mixture, right? Okay, I add 25 cm3 of the acid, I add 25 cm3 of the base. The 50 cm3 is made from the summation of volumes, correct? Then the way to calculate will be via this. So look at the one on the further away. Okay, for energetics kinetics experiment involving one reaction mixture, usually you will sum them because they add up to the total volume. Is that okay? Okay, now when do I use this? Separate out each of them. When the volumes are related to each other via multiplication or division, correct? So for example, I pipette out 25 cm3. Okay, the amount in this 25 cm3 and the titration that I use is related via a times and divide of the stoichiometric coefficient. Do I make sense? Correct? If it's a 1:1, then the amount will be the same. Then from there, I can derive roughly what is the titration volume. Correct? So when they're related via a times and a divide, okay, then you will separate them out like this, which is usually what you see on the left side. Okay, titration experiment involving more than one volumetric glassware. So the pipette, the burettes, they are related via stoichiometric coefficient in a times and a divide manner. Are we clear on this? Clear, okay? So please make sure you write this down. Okay, so let me give you the first example. Some of the percentage uncertainties. Example are people. You will see your burette, your volumetric, your pipette, your burette, okay? All these are related to each other via a times and a divide in their amounts, okay? So we will separate them out. Okay, so this one is the A over VA plus V over VB plus C over VC. Okay, so you see, find all of them, then I sum all together. Find individual and you sum the individual together. Yes. Can I continue? Okay, this one you have a good idea, right? Alright. Okay, commonly we see this kind of calculations in VA. Now, this is the other one where you sum them, okay, before or over the total volume, like this. Yeah. Plus B plus C over VA plus VB plus VC. Okay, so you see that they are added to the same test tube here. Okay, so it's a summation of volume, so therefore we sum them all over the total volume. Okay, now there are multiple practices with different kinds of percentage uncertainty. So when you are reviewing, you should have seen them. Let's continue. Okay, can I continue? Right, okay, now next one, let's go on to Enoch. Now this table is provided to you. This is the only thing that you will get. Okay, so the two-sided yellow paper with this. Okay, now gentle reminder, there are 11 cation ions, 8 anions and 6 gases. You need to know how, okay, their observations will look like. Okay, the identity and stating of evidence. Okay, so please make sure you know how to record observations. Okay, these are also reminders to the colors of the cation ions. Sometimes we don't see them as much. Okay, Fe3+, usually you see them as yellow. Okay, the red brown is the hydroxide, which is the PPT. Okay, Chromium 3 plus is a very dark shade of green, but it's clear. So under the light, you can see a very clear dark green color. Okay, copper 2 plus is the very famous blue. Most of its compounds are also blue because of the Cu2 plus. Okay, so when you see blue, you should think of copper 2 plus. Alright, I'm going to continue. Most importantly is the Fe3 plus. Many of you think it's brown, but it's not, it's yellow. Let's continue. Now, these are some reminders for you. Okay, when I am writing my evidence, please make sure you state the precipitate identity. Okay, look out for hydroxides that oxidize in air. How many hydroxides oxidize in air, people? There are only 2 of them. Who are the ones that oxidize in air? Fe2 plus Fe2, iron 2 hydroxide, and manganese 2 hydroxide. Okay, one will become the red brown. You can see at the walls of the test tubes or on the surface. The other one is this off-white that will also turn brown. Okay, so this off-white, when you're not sure whether is it manganese, look out for the brown. Okay, it browns really fast actually. Alright, they are here. On contact with air, turns brown on contact with air, turns brown rapidly on contact with air. Okay, identity of complexes, sorry, I'm going to annotate here. Not required in not required in evidence. Okay, I don't need you to state this in the evidence. It's more of in like, for example, KSP explanation. So why your PPT dissolve? Okay, when you write the equation, naturally you need the complex identity. Okay, required in KSP equations and explanation. Questions? Okay, now these are not all the complexes. These are the complexes that is in the table, okay, for the cations that are in the table. Alright, frequently they can give you an unknown and they can also make the PPT dissolve in exams. Alright, so remember, the complexes you see in KSP notes as well as transition metal notes, you should know them. Can I continue? Mostly done. Okay, great. Let's continue. Now, next one. This one is an important reminder for you. Carbonate is very commonly added. Okay, there are 3 possible outcomes. The first one is you have PPT, no carbon dioxide. That suggests a +2. Okay, so this is the PPT identity. Okay, don't write first. Let me finish first. Don't write. The second one is you have a PPT and you also have carbon dioxide, suggesting it's acidic. Okay, so this must be a +3. Now, I'm going to take this opportunity to remind you, for a +3, the PPT is a hydroxide. Okay, no more carbonates, so I should not see stuff like this. This is atrocious. Okay, carbonate is fully destroyed because reacted with the acid, right, to produce the carbon dioxide. So you have no more carbonate left to form the PPT. Alright, so the PPT will be that of a hydroxide. Please make sure you note this when you're writing later. Alright, now the last one is this. It is only carbon dioxide with no PPT. Okay, so likely your H+, which again they love to test. Okay, this is very easy. Just use an acid as the reagent. Okay, you can start the copy. Okay, they love to test you on H+, because it's very easy to prepare the solution. It's just one of your acids, right? Why can't I start this? Make sure you memorize the equations also. These two is super important. These ones. Okay, so you see your periodic table equations, your inorganic equations, people. So you also have to study your periodic table before you come. Like why the cations are acidic. Okay, make sure you write down carbonate, cations with carbonate, and list down the 3 scenarios. Okay, PPT, no carbon dioxide, it must be an M2+. Okay, the PPT is a carbonate. Alright, then you have PPT with carbon dioxide, suggests it's acidic, it's a +3. The PPT is a hydroxide, then write the 2 equations there. Okay, and finally, no PPT but carbon dioxide, acidic, so H+, likely H+. Make sure you copy all 3 scenarios, people, as well as the equation. Make sure you also copy the ions correctly. Questions? Can I continue? Okay, let's continue. Now, more inorganic, okay, this is a reminder for evidence, okay? When you are asked to write evidence, so you write down, firstly, test number, secondly, PPT, identity, and color. So, for example, off-white PPT of manganese 2 hydroxide, turning brown on contact with air. Okay, number 3, if there is gases, please make sure you write the gases. So it is identity plus gas test. Carbon, effervescence of carbon dioxide, which forms a white PPT in lime water. Now, this one I don't need, okay? Just look out for solubility in excess. Okay, I think I should write a bit more, okay? Identity, color, in contact with air, okay, and solubility in excess. To form what? Okay, to form what is really irritating. You guys always stop at the excess. You always forget to form a colorless solution, okay? Because they don't write it in the table. Just make it clearer. PPT, number 1, I want the color. Number 2, I want the identity. Okay, number 3, I want the in contact with air, if applicable. Contact in air, if applicable. And of course, I want the solubility in excess to form what? To form what solution? Okay, for example, in test A, okay, off-white PPT of manganese hydroxide, okay, turns brown on contact with air, insoluble in excess. Blah blah. Okay, now, yes, Mia? Only in evidence. In the normal observations, you only record the observations. In the normal one, right, we only identify the gas. Okay, that is a good point raised. Okay, people, in normal observations, you only identify gases, and they will be in the instructions: test and identify any gases evolve. Okay, but in the evidence, you will need to write the identity of the PPT and of course the rest of the gases as well. Questions? Okay, let's move on. Now, next up, organic. Organic, I have 4 of them. Shh. This is the first one, 2,4-DMPH, okay? Please remember, while in theory it's written as orange, usually you will just see the yellow, okay? It's fine, you will still conclude orange. Okay, that suggests you have a carbonyl compound. Carbonyl compound, people, or aldehydes or ketone present, and the reaction is condensation. Usually you cannot remember. Tell me what, oxidation or don't know what. Okay? 2,4-DMPH, orange, but it may appear yellow, is still positive. Alright, next one. The next one is Tolan reagent. Now, Tolan reagent are usually, they will not give you the Tolan. They will ask you to prepare the Tolan. Okay, so how to prepare the Tolan? Of course, they will guide you more than this. There will be these followed by excess NH3. Just remember, Tolan is a saturated solution of Ag+. Okay, you should not have PPT in the Tolan reagent. It's a saturated solution. So dissolve, and then after that you decant or you filter away. Okay, Tolan usually they won't give you, they will ask you to prepare, which is like what you did in practical, prepare the Tolan. Okay, silver mirror is the positive observation, usually with heating. Alright, aldehyde present and it is an oxidation. Okay, again, cannot remember what it is. Yes, correct. Just write orange. Yeah, I mean, you stick to the theory. Questions? Okay, let's continue. Now, next one, iodoform. Okay, this is the last two already. Iodoform, very commonly tested also. Okay, if you also recall, we did iodoform, and sometimes you don't even need to heat. Okay, so heating not always required. Alright, NaOH followed by iodine until yellow PPT. Again, it is oxidation. Okay, it's a very pale yellow PPT. Okay, so you record yellow or pale yellow, it's fine. Okay, anyway, the gist is the yellow. Alright. Okay, just note that you may not need to heat, people. Okay, if I see the yellow, then I just write record. But if I don't see the yellow, make sure you heat to see if the yellow appears. Okay? And of course, water bath for people. No direct heating. Now, the last one, of course, is the one that is readily available. K-4, you see it for your QA, and you see it for your VA as well, okay? K-4, you must heat. Without heating, it will not decolorize. Okay, when it decolorize, it should ideally become colorless. Sometimes there is a very pale tinge of yellow, it's fine. Okay, as long as the purple goes off, you will conclude positive. Are you clear on this? Okay, make sure this one, your water bath is hot enough. Okay, again, if it's pale yellow, it's fine. As long as the purple goes off, we will conclude positive. Questions? Questions? No? Okay, now then, please make sure you're well prepared for the Wednesday's practical. That is your one and only trial before the final practical in October. Okay, now we'll take a mental break. Let's resume at 10:14 and then we'll continue with the TY.